This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai Studies. A link is in the description box below. Does the following series converge or diverge? Well, we have a bunch of tests to test for convergence, and because I see an exponential, so any number raised to the nth power, so e is the number raised to the n power, we're going to use ratio. So remember that ratio is for factorials and exponentials. So the rule for the ratio test is based on the limit as n approaches infinity of the ratio, so a fraction of your sequence, but wherever you see n u out of 1 divided by your sequence, take the absolute value of that, and that's equal to a limit, or in Rutgers we call it rho, even though it's a p. And so the rule is if rho is less than 1, rho is greater than 1, rho is equal to 1. I kind of think of it as a number line, like negatives, then positives, and then equal is just like miss. So I think of it in that order. Then this series converges absolutely, diverges, or the test is inconclusive, so you try another test. So we're going to take the limit as n approaches infinity of the absolute value of our sequence, but wherever we see n we add a 1, so that's going to be n plus 1, and then e to the n plus 1 divided by 5. So this is this, and then we have to divide by the sequence, which is this, or we can multiply by the reciprocal, which is just you flipping the numerator and denominator. Now the absolute value of this is this, because n is equal to 0, meaning all the terms in this series will be greater than or equal to 0, so they will be positive, and so no need for the absolute value. But technically, the absolute value of this is this, and because we use the absolute value, we have to use these rules. So once you set it up, always switch your denominators so that similar things can be together. So now we can see that it's clear that this is e. Another way to rewrite it is n plus 1 divided by 5, and we know that we can split this up. So this is e, n divided by 5 plus 1 divided by 5, and that can be split up into e to the n divided by 5 times e to the 1 divided by 5. So basically, algebra. So if we have e to the n divided by 5, and then in the denominator we have this, then we can see that these cancel out, and we're left with 1 over e to the 1/5. And then this is already a rational fraction, so we know that we can divide every term in that fraction by the term with the largest power in the denominator, so that's n to the first power. We're going to divide everything by n to the first power. This becomes 1, this becomes 1, so we're just left with 1 plus 1 over n over 1, which is just that, times 1 over e to the 1/5, and then we can plug in infinity. So 1 whole divided into infinitely small pieces becomes infinitely smaller, so small, it comes out to be 0. So 1 plus 0 is just 1, and then we have this. So we have that the answer is this. And since we have 1 and we're dividing it, we're making it smaller, then that's going to be less than 1. The whole fraction is going to be less than 1. And so because rho is less than 1, then we know that this series over here converges absolutely. But they didn't ask us if it converged absolutely, they asked us if it converged or diverged, period. So how do we get to this part over here? We use the absolute convergence theorem, but first, let's write our conclusion. Since, and then you just take the first limit that you write, so this is equal to 1 over e to the 1/5, which is less than 1. The ratio test implies the given series converges absolutely, but again, they didn't ask us if it converged absolutely, they asked us if it converged. So we use our number 2 tool in our toolbox, which is the absolute convergence theorem, that says if we have any series that converges absolutely, which we do, we have a series that converges absolutely, and we can say that that same series converges. So we're going to say, and absolute convergence implies convergence by the absolute convergence theorem, so the given series converges as well. So the answer is that this series converges.